All right, we're still working in section 11.8 vectors. Now we're on page 3 of the notes. Page 3, I want to introduce a vocabulary term that I use when talking about vectors, and that is the term resultant. Okay, a force, velocity, or other vector quantity that is equivalent to the combined effect of two or more component vectors acting at the same point. That is called a resultant vector. And that often happens when we add two vectors. So what we're going to get some practice with here is adding vectors, looking at the first looking at the sum of vectors graphically, and then determining the net component form, magnitude, and direction of the resultant, or of the sum of the vectors. So I've given you 4 vectors here. They're given in component form, and we're going to look at combinations of them. So here we go with the first one. We're going to look at the vector a plus c, and I'm going to just call it vector v. And let's go ahead and graph each of the vectors. So we'll start by graphing vector a. And vector a has a horizontal component of 2 and a vertical component of 3. So that's vector a. And vector c has a horizontal component of 4 and a vertical component of -1. And notice when I'm lining these two vectors up, I'm starting vector b, excuse me, that's vector c, typo. I'm starting vector c right where vector a ended. And what I then get is a dog barking in the background, or vector v, where vector v is the resultant of a and c. Okay, so let's go ahead and take a look at what vector v is, both, and remember here there's 3 things we have to find about vector v. We have to determine the component form, the magnitude, and the direction. So 3 different things we have to figure out for vector v. Okay, let's start with the component form. Vector v equals vector a plus vector c. And to find that component form, well, we could count it up graphically here. That's easy enough to do. But sometimes that's not convenient, so I'm just going to show you how you would do that. You just add the components, horizontal and vertical, for a and c. So vector a has a horizontal component of 2. Vector c has a horizontal component of 4. Now for the vertical component, vector a has a vertical component of 3. Vector c has a vertical component of -1. So the result is we have a component form of vector v that is 6, 2. And you should be able to see that graphically by counting over 6 and up 2 to get from the origin, or the initial point, to the terminal point of that vector. Remember in the first video I talked to you about the tail to tip vector addition method. So if we're adding vectors a and c, the resultant starts at a, that's the tail of a, and goes to the tip of c. And there's another way to add those graphically. If you want to learn about the parallelogram method, go ahead and check your textbook for information on that. All right, let's go ahead now and look at both magnitude and direction of vector v. Magnitude of v is going to be the square root of the sum of the squares of the horizontal and vertical components, and that is the square root of 40. If you really want to put that in simplest radical form, feel free to write that as 2 root 10. Okay, now the angle. Well, this one's pretty easy because we're in quadrant 1, and we know quadrant 1 plays nicely with the inverse tangent function, so we can say that angle for vector v is just the inverse tangent of the vertical component divided by the horizontal component. And that gives us an angle of about 18.4 degrees. Okay, folks, let's move on to part B of this problem. This time we're also combining a couple vectors, except we're doing vector subtraction. I'm going to also call this vector v, which will be vector a minus vector c. And if you're okay with this, I'd really like to keep this as vector addition. So it's going to be vector A plus the opposite of vector C. Now we already had vector A drawn in our previous problem, so let's go ahead and add that back to our new picture. Vector A had a horizontal component of 2 and a vertical component of 3. And vector C, let's go back up and take a look at this. Vector C had a horizontal component of 4 and a vertical component of -1. So if I'm going to add the opposite of that, it means I have to have a horizontal component of -4, 1, 2, 3, 4, and then a vertical component of +1. So it's going to look like that. And it appears that my little name for vector A is going to get in the way, so I'll move that out. And let's go ahead now and draw the opposite of vector C. Looks like that. And that's the opposite of vector C. So the resultant vector there, which we're calling vector V, looks like that. So now let's show the math to get the actual horizontal component, the component form, magnitude, and direction. So vector V equals vector A plus the opposite of C, and that's going to be 2 minus 4 and 3 plus 1, which gives me a horizontal component of -2 and a vertical component of +4. And you should be able to see that graphically. Vector V goes 2 to the left and then 4 up. The magnitude of vector V is equal to the square root of 2 squared, or -2 squared, which turns into a positive value. Square root of that, which equals square root of 20. And I'm okay if you leave it like that, but if you feel so compelled, you may turn that into 2 root 5, which is the simplest radical form. I've factored out a perfect square factor of 4 and taken the square root of that. Okay, now we have to think about the angle theta for this vector. Now this one isn't as simple as the last one. Remember, the angle theta is this angle right here. It's the angle between the positive x-axis and the vector. Well, that angle is in quadrant 2, so we can't use inverse tangent directly. What we can do is modify the angle pi by subtracting the inverse tangent of 4 over 2. And let me show you what that looks like. Pi minus the inverse tangent of the value 4 here divided by the absolute value of this. And that's about equal to 116.6 degrees. And some of you might be wondering to yourself, why did he use +2 instead of -2? I'm so confused. Well, remember, I was adjusting the angle pi by this little missing piece right here. And this little missing piece right here has an angle of inverse tangent of 4 divided by 2. And if you're confused as to how to adjust angles in quadrants 2, 3, or 4, I would encourage you to look up the reference page that I put in the Chapter 11 folder. Okay, so what I'm going to do now is move on to Part C, and I'm going to just grip it and rip it through this one really quickly because we've already done a couple examples.
Hey, Dad. Dad.
Okay, folks, there you have the solution for part C. We have a component form of -6, 7, a magnitude of square root 85, and a direction of approximately 130.6 degrees. All right, let's move on to this last one, part D. This one's kind of crazy. We actually have the resultant of 4 different vectors. So we've got to combine, we've got to do multiple vector additions here, and I'm going to show you how that you can do that graphically, and then we'll look to see what it looks like algebraically. I'm going to go ahead and take whoa, extreme close-up. I'm going to go ahead and copy down those vector values again so that we don't have to keep scrolling back up to the top, but there they are. So I'm going to start by graphing vector A first. So vector A has a horizontal component of 2 and a vertical component of 3. So there's vector A. I'm going to add to that vector B, and vector B has a horizontal component of -1 and then -5. 1, 2, 3, 4, 5. And I'm lining each of these vectors up tail to tip. From there we have, we're going to subtract vector C, so it's like adding the opposite of C. So if I will add -4, horizontal component of -1, 2, 3, 4, and then add -1, so that's like adding +1. Subtracting -1 like adding +1. There's the opposite of vector C. Now I have to do the same thing with D. And D is the vector -5, 2. So that'll turn into +5, 1, 2, 3, 4, 5, -2, which ends up down here. Kind of a crazy picture, but that's what we have for doing this, the resultant of those 4 different vector operations. And that resultant will look like this. So let me try and label these for you. We started with vector A, and then we had vector B, then we had the opposite of vector C, and we had the opposite of vector D, which gave us a final vector of V. Okay, and it's pretty easy to see that V is going to have a horizontal component of 2 and a vertical component of -3, but let's just show the math that gets us to that. So vector V is going to be equal to 2 plus -1 minus 4 minus -5. And for the vertical component, I have 3 plus -5 minus -1 minus 2. And that gets us the following. Okay, so let's see here. We got 2 plus -1, that's 1. Minus 4 is -3. Minus -5, so that's -3 plus 5 gives me a +2 for my horizontal component. For my vertical component, I have 3 plus -5, that's -2. Minus -1 gets me, that's +1, it's back to -1. Minus 2 from -1 gives me -3. So there is the horizontal and vertical components, the component form of vector V. Now let's go ahead and look at the magnitude of vector V. The magnitude of vector V will be equal to 2 squared plus -3 squared, all square rooted. Let's see, that's going to be 4 plus 9, or the square root of 13, exact answer. How about the angle? Well, it depends. If I just say theta equals inverse tangent of negative 3 over 2, I'm going to get the following value. I'm going to get negative 56.3 degrees. And remember, inverse tangent works in quadrant 4. It just gives us a negative output. And when I say inverse tangent works, I mean using the y over x values from the component form of the vector. But what if WebAssign says that you have to have theta as a positive angle between 0 and 360 degrees? Well, I just have to subtract, I have to add this negative 56.3 to 360, and that gives me an answer of 303.7 degrees. Okay, and I'm guessing that WebAssign is going to ask for this positive angle instead of the negative one. So how could you have got that directly? Well, you could do this. Theta equals 2 pi plus inverse tan of negative 3 over 2. Plug that into your calculator, convert it to degrees, and you're going to get that 303.7 degree number. Okay, folks, that's it for this side of the notes. I hope you're looking forward to page 4.